Okay, everyone, welcome back to the Rust Embedded class. And then sorry because we missed a week, but we are going to do as much to cover up for that week that was missing. And Professor Brad was in China for a big conference. And aside from that, I think I was not really feeling fine. But now I'm okay. So once again, thank you and welcome. Let's sit back and watch Professor Brad teach us about embedded Rust, and then let's get rusty. Cheers. Thank you very much.
Yeah, welcome everybody. Sorry about all the interruptions and delays over the past couple weeks. It's been a really busy time for me. I've had two big conferences, and my son has gotten married, so it's been a big time. But we're back to running regularly, and I don't see any interruptions likely from here on out. I did post a little half-hour video with some of the stuff we're going to be talking about today and some sort of bonus stuff that I don't plan to cover today. So if you get a chance and haven't yet, please check that out. I think it will be good. So yeah, I want to talk today a little bit about actually the details of how the instructions we write in a Rust program make it to being making the board do something, right? Making our little microcontroller board actually do a thing. And so that's kind of the priority of the day, is to understand all that. So let me start with a really quick overview or review of what we actually did in that video. It's going to be the lightning speed, and I'd really encourage you to watch the video to get the whole thing. Remember that our board has a bunch of hardware on it, right? And maybe the most important piece of that hardware is the little microcontroller that lives on it. Let me go pull up the manual for that. So the critical stuff, which is linked from our course repo, is the microbit itself has a schematic and the microcontroller has a manual. So let's look at the microbit schematic first, because I think that's an interesting thing to look at. If I'm assuming none of you have seen a schematic, well, a few of you have seen a schematic before, but if you have, that's fantastic. A schematic is a diagram that describes how what the hardware all is on that board, on our board, and how it's hooked together. You'll notice that, oh, sorry, let me switch to the actual thing so you can see it. So this is the schematic for the microbit. It's probably a little hard to see. I've made it as big as I mostly can. And you don't need the details at this point, but the point is that each of these little blocks in the schematic is a piece of how the hardware is hooked up on our board. And to talk about that, we probably need to start by talking a little bit about electricity. Again, I assume some of you know all this, and I'm sorry if I'm boring you, but electricity is it flows through a thing and makes it do something. So in the case of our board, we put 5 volts of electricity on the power connector, on the USB power connector on the board. And that flows through the board, making it do stuff. And then it comes out the ground side of the power connector. So we have two things with electricity. We have voltage and current. And voltage is how hard the electricity pushes, and current is how much of it is flowing. And for our little microcontroller, like I say, the USB connector is at 5 volts, but of pushing power, of voltage. But there's a little circuit just inside the board that converts that to 3.3 volts, and the whole board itself runs at 3.3 volts. This is a very tiny voltage. There's no danger involved with any of it, because it's not any more powerful than a couple batteries. It's just not a thing. And electricity flows through copper wires. They don't get in the way of it. They don't really do anything to it. They just guide it where it wants to go. And then, like I say, it flows through the components in our circuit. The amount of current that flows through is, decides how much power things use.
Please, hello, Professor Brad. Please, we're
Yeah.
not seeing your screen. I don't know if you're sharing your screen.
I know. I wasn't trying to show my screen. I was just talking for.
No issue. Thank you.
Thanks,
Thank you.
though. Yeah. And so but I can show you, it's not a big deal. Let me zoom in on, well, this is the circuit that I was talking about. This actually takes the 5 volts from the USB connector, and it puts it through all these parts that you don't really need to understand. And out this other end comes 3.3 volts that goes to the rest of the board. And so this diagram shows how the wires connect all the components on this part of the board. And so, all these things together, it's a lot, are all the components of our circuit. The things we'll be most interested in today are this piece. This is the LEDs on the board. Remember that the board has these little lights on it in a 5x5 grid. Yeah, that's these parts on the board. These little arrows with a bar are called diodes, and you can tell these are light emitting diodes because the arrows coming out of them are supposed to represent light. And so it turns out if I put 3.3 volts here and make this side of the circuit be ground, then the diode will light up. It will emit light. Notice that these wires aren't connected because there's not a blue dot here. These are just disconnected. So this just crosses over this other wire. So the point is, if I can get the row 1 wire to have 3.3 volts and the call 1 wire to be ground, then we can light up that upper left LED. That's how we light up our light. Well, how do I do that? Well, these wires are also connected to our actual microcontroller. If we go down here, we see that the row 1 wire is connected to something called P0.21, and the call 1 wire is connected to P0.28. And so if we can tell the microcontroller to turn on the bit, make the bit at P0.21 be an output of 3.3 volts, that pin, and we can tell the microcontroller to make the pin P0.28, the wire there, be accept electricity, that by grounding it, then we get the LED on. So that's electrically what we're trying to do. That's exciting. And to get how we're going to do that, let's take a look at the other key piece here, which is the actual microcontroller manual for the microbit. Let's see. There it is. And the microcontroller manual, here I've scrolled down to the part we're going to actually care about. The microcontroller manual is huge. It's 620 pages, and it tells you everything about the little computer on our chip. It is absolutely an immense thing to read, but it's definitely worth grabbing and reading. Here's the summary of all the things that are on our microcontroller chip. We have this is what's called a system on chip. So it has a computer. That's this ARM Cortex processor that you can barely read here. But it also has a whole bunch of other devices on the chip, and we'll be playing with a lot of them during this course. It's got a Bluetooth radio. It's got a bunch of memory. both program memory and data memory, flash and RAM. It's got a whole bunch of devices, so many sort of onboard pieces of hardware that do things. And the one that we're going to be interested in today is what's called the general purpose input output pins, the GPIO pins. And every microcontroller has GPIO pins. The GPIO pins on our microcontroller are arranged into two so-called ports. Each port has, the first port, port 0, has 32 pins, controls 32 pins, and the second port controls another 9 pins. And these are super fancy. It turns out that these general purpose input output pins can be configured either as inputs, where the microcontroller reads them, or as outputs. The microcontroller, puts a voltage on them. Today, we're going to be putting a voltage on them. We're going to put either 3.3 volts or 0 volts to drive our LED. And so there's a lot of detail about how this works that today I'm going to ignore. It's in that supplementary video I mentioned where we actually go into a lot of detail about how all the registers and stuff. But very briefly, the important idea here is that there are these locations that look like they're in program memory that you don't, when you store into them or read from them, it doesn't actually put stuff in memory. Instead, it makes the microcontroller's stuff do things. And so there's a whole bunch of memory locations described in this manual that allow you to change what's going on with the GPIO pins. So by manipulating manipulating the device registers in the computer, which are just memory locations, you can make the pin be an output pin and make it be an output pin with the voltage we want. So that's what we're going to do. That's what's going on at the lower level. And both the microbit schematic and the microcontroller manual are definitely worth looking at, even though a lot of it's going to look kind of confusing at this point, unless you have some hardware background or have worked with microcontrollers before. Just to see what's going on. They are kind of the ultimate source of truth about what's happening with this stuff. So it turns out that what you want to do when you first get a microcontroller board, pretty much what you always want to do is to make it blink an LED on the board. That's just sort of the first thing. It's sort of the hello world of embedded programming. Is you get a board, you want to make an LED blink. And that's because if I can make an LED blink, that proves I understand how the GPIO pins on the board work. It proves that I know how to manage time a little bit so that I can get it to blink instead of just standing still. By the time I demonstrate I can do that, then I'm very happy that I can go on and start to do more complicated things. Like I say, it's like hello world for a programming language. So, but for us, it's the hello world of hardware. So that's what we're going to concentrate on today, is taking that LED in the upper left-hand corner of our microbit, the LED up here, and we're going to make it go on and off once per second. That's our plan. And to do that, what we will do is we will go look at some code. I'm going to day 4. I can't believe it's only day 4 already, but it's just day 4. I'm going to go look at this Blinkies directory. We call that a Blinky. That's the name of this program that blinks an LED. You might wonder, what happens if I get a board, some other microcontroller board than the microbit, and it doesn't have any LEDs? And the funny part is that never happens, because always whoever designs the board puts an LED on it, basically just so that can be able to blink that LED and make sure everything's working. And so it's almost impossible to find a board without an LED to blink. And sure enough, this one has 25 of them. That's a little unusual. So let's look a little bit at some of our Blinky programs. One of the things about Rust that you can do is if you have a source bin folder in your project, then you can put multiple programs in there and decide which one you want to run later. We're going to start with something called the Peripheral Access Crate, the PAC. So what we're going to do is do Blinkies at 3 levels of sort of abstraction, right? We're going to do a Blinky that's very, very low level that you wouldn't normally write, and a Blinky at a middle level that is something you might write, and then we'll do a Blinky at the highest level that you'd probably write for bare metal. So we'll get to see how this works, all the levels, and every program we write is going to work with some combination of these 3 levels, and so I think it's worth talking about. The first level is the Peripheral Access Crate level. The PAC, the Peripheral Access Crate, or the PAC, is a piece of Rust, as a Rust library that is specific to your microcontroller, in this case to our NRF52833. And what it does is provides you some abstractions for working with it. So let's talk about all this blop at the top later. Here, the Peripheral Access Crate contains some structures that represent pieces of the microcontroller, and those are called the peripherals. And so we're going to get those peripherals and store them in a variable, those peripheral structures, and store them in a variable. We do it with a take and an unwrap, which is weird. This is weird Rust. What's going on here is that the take takes ownership of the peripherals, and it returns a Rust option type. If it's able to take ownership of the peripherals, it returns the peripherals, and then you can unwrap the option to get at them. If it doesn't manage to get a hold of the peripherals, maybe because somebody's already taken them, then it returns none, and this unwrap will panic. Your program will stop. And so what we're doing here is just making sure that we're the only place that can manipulate these peripheral structures. Now we use a it's interesting. This says it's all PAC, but there is some stuff being used from the HAL here. I'm not really sure why. We could do this at the PAC level. I'll have to go back and fix this later, but this is sort of part PAC and part HAL. And now we're going to go ahead and use the next layer up, the HAL layer, the hardware abstraction layer, a little bit to go ahead and get at the pin structures that we need to do stuff. So here's the row 1 pin and the call 1 pin. So what we're doing here is we're saying set up those so that they're outputs, and start the row 1 pin as a plus 3.3 volts. That's what GPIO level high means. And start the call 1 pin at a low level, GPIO level low. And now we're just going to do the following. We're going to wait for half a second. We're going to turn the row 1 pin high to 3.3 volts so the LED lights up. And that's what that is. What is this unwrap here? This unwrap here is maybe somehow the microcontroller could fail to set the pin high. That can't actually happen with our microcontroller, but it could on somebody's. So we're checking that. Again, this returns an error type. And if there's an error, then the program will stop. But it won't. It will never return an error for us. And so we're okay. And then we'll wait another half second, and then we'll turn the row 1 pin to 0 volts. And by turning the row 1 pin to 0 volts, so we're going to do the thing. We're going to, let's go back up here. We're going to put the row 1 the call one pin is always going to be low. It's always going to accept electricity. It'll be ground. The row one pin will turn on for half a second, plus 3.3 volts. Then it will turn off for a second, 0 volts. When it's on, the electricity will flow through here and it'll light up. When it's off, electricity won't flow and it will go dark. And that's how we're going to blink the LED, is like that. So let's prove to ourselves. Oh, but the last thing we need to talk about is this weight. See, one of the problems with microcontrollers is you can't ask the operating system to do anything because you don't have an operating system. Normally, the way you would just stop for a bit and let time pass is you would call some operating system routine and say, hey, don't wake me up again until time has passed. Call that sleep in most operating systems. We don't have any way to sleep. And that's a little frustrating. What we can do, though, because we own the whole microcontroller and nobody will stop us, is we can so-called spin weight. What we're doing here, this special variable underbar means just I don't care, ignore, the variable. I don't need it for anything. That's what's called a pattern. And this says 4 million times. Notice that Rust numbers can have underbars in them. They're just ignored, but it makes it a lot easier to read. So it says for 4 million times, do a no-op. What's a no-op? It's literally a microprocessor instruction that does nothing. We can, it says, spend a cycle doing nothing. That's all it does. So we're going to spend 4 million cycles in this loop doing nothing. And it turns out that on our particular microcontroller on this particular day, it's about half a second to do 4 million no-ops. It's very rough, but it's about that. And so this is how we're going to delay, is we're just going to sit there doing no-ops, run 4 million instructions that don't do anything, and then we'll have waited long enough and we can change our thing. Sorry, I'm noticing I'm not following the chat very well, and I apologize for that. I hope that everybody who's there, I guess there's only 3 people there right now. No, that can't be right. Comments, where are they? Oh, I'm sorry. I didn't see the chats yet. Let me go back. The schematic diagram. Yeah, it's linked from, I'm pretty sure, from the top level page. Let me go back and find for sure. Oh, no, still not high enough. Nope, it's too high. In the resources here are a couple of links for the microbit 2, and one of them is for the schematics, and one of them is for the manual. So that's where that stuff is in the README of our repository. You can find these links, and somebody can copy paste them if they like there. So yeah. So we're spinning here, doing nothing for 4 million cycles, and then we change the state. And this loop here, remember, the program can never return because we don't have any operating system to return to. But here we make this loop do something useful. This spin weighting is not the best idea in the world, because if we're running on battery, every one of those no-ops consumes some electricity to execute, and so it gets pretty expensive. Other than that, it's fine. No, it's not like we're keeping anybody else from doing anything. We own the whole computer. In normal computing, you never, ever want to spin weight. Here, it's kind of gross. It's not very accurate, and it consumes electricity, but it's not the end of the world if you spin weight. It's a common thing to do sometimes. So let's run this. Let's see if it actually does the thing. That's always a good idea. But before I do that, actually, let's take a look at our setup again, because it's a pretty fancy setup. Because we have a bunch of different kinds of blinkies, we have a bunch of different crates involved here that we're using with this. This is our cargo.toml that says how to build the program. In particular, we need this Cortex-M RT crate. I think we've talked about this before because that crate provides the entry macro that sets up this function as the place where our program starts. We also need the Cortex-M crate with inline assembly because that's where we get this no-op instruction. This is basically a function that executes no-op. So yeah, we need that. This is from the so-called embedded HAL traits. We'll talk more about this in the future, but it lets us get at the output pin and set it high or set it low. And then these HAL crates here are just used in the pin setup, basically. So that's what's going on there. And the other thing that you might remember we have around here somewhere is this, which says, oh yeah, we're going to build for our microcontroller. And when we run it, we're going to run it using ProBars. And by the way, we kind of need to have the linker be able to work and this thing be able to work. So this is just boilerplate, but it's kind of necessary boilerplate for what we're doing. So having seen all that, I think we understand everything. Let's actually run this. And now you can see the thing starting to blink, right? And of course, again, like last time we talked, the ProBars crate on the host is the ProBars program on the host is waiting for the microcontroller to talk to it, but it's never gonna. So we can just stop that, and that doesn't hurt anything. The program keeps running. Oh, and by the way, if I hit reset, the program starts running again after a reset. And if I power it off and on again, when I power it back on, the program starts running again. The program's sitting in flash memory. It's going to run every time the computer starts up. And that's a little annoying because we'd kind of like to turn that LED off maybe. Unfortunately, the only way to turn it off is to upload another program that doesn't turn the LED on. So what we're going to do here is go back to here and run this program, which turns off the LED. There. Now we can see that it's not running anymore. But that's super annoying. But that's how we're going to have to do it. So that is a blinky. It blinks things. And that's like, it uses the PAC peripherals, the peripheral access crate peripherals. That isn't what you'd normally do. But when we write code at the PAC level, we're writing at a level that's just above poking at the registers directly. And that video that I gave you shows how to just poke at the registers directly, but we never do that in Rust, basically. The peripheral access crate provides a very low-level interface, and we actually ended up using the HAL interface on top of it anyway. Let's look at we're really using the HAL. Does it look any different? It's really actually pretty much the exact same code. It's just that we dig the PAC out of the HAL crate. So this code isn't actually any interestingly different in terms of that. What we did do with this HAL code is, remember we had that terrible spin weight in it? It turns out that among the 30 or so peripherals that are inside our microcontroller, one of them is a so-called timer, which takes care of time. And it turns out the HAL, the hardware abstraction layer, which is the layer above the peripheral access crate layer. Let's put some notes somewhere, actually. I don't know. Right. So there's the sort of the peripheral access crate. There's the device registers. There's the peripheral access crate or PAC layer, which provides a REST interface as a library to those device registers. There's the hardware abstraction layer, the HAL, which provides a cleaner interface to the PAC crate that supports stuff in an easier to use way. And then there's the so-called board support package that we'll look at in a minute. And the board support package is this is just customized to our microprocessor. This is customized specifically to the microbit board that we have. And so this provides all the conveniences we can for working with the microbit. And after today, that's mostly what we'll be working with. So there we are. But today we're now at the hardware abstraction layer here in the middle. And right here, we're just going to have, so we go into the PAC crate, right? We got all the peripherals out of the PAC crate, and we're using the GPIO peripheral like we did before, but we're also using a timer peripheral. It turns out the NRF52833, our microcontroller, has 4 of these timer peripherals, and each one can be used for delaying or for making something happen after a time or for a whole bunch of different things. We're just going to use them as simple delays. So once we've gotten control of a timer peripheral and set it up as in a way that the HAL can work with it, now instead of our spin loop, we can call delay milliseconds 500 milliseconds, half a second. And now it will delay for exactly half a second. And during that delay time, it won't be running no-op instructions. It'll just be in a low power state, waiting for the timer to wake it back up. So this is by far a better way to delay for a half second than our stupid spin loop, is to actually use the hardware in a way that it was intended to work, to actually do delays. So again, the rest of this is the same as it was before. I don't think it takes much explanation. Let's run it. Let's flip back to the view where you can see it run. A little surprised that it's needing to rebuild. I thought I had this built already. Rust compile times can be long, and I'm sorry about that, but it's really first compile times. After this, it should go very fast if we change the program. And this time, it really does go on and off at exactly half a second. If you time it with a stopwatch, 1 second per blink, basically. If you time that with a stopwatch, you could use that to, time cooking or whatever. It's absolutely an accurate 1 second blinky. And so the HAL layer is really, really useful if you are working in a generic way across many boards with the same microcontroller, or even the ESP32. There's 2 flavors. Sorry, I missed your question. There's 2 flavors of ESP32. There's the ESP32 well, there's three, but really the two that matter are the 32C series and the 32S series. The S series uses a weird instruction set called Espressif, that's by the company that makes the chips. And Rust will work with that, but it's a little fiddly. There's some things you have to do because the Espressif compiler backend hasn't made it into the official Rust release yet, so you got to use an alternate backend. The C series are RISC-V parts. They use the RISC-V instruction set, and for those, the support's very good, works fine. So Espressif, the company that makes the ESP32s, is now officially supporting Rust, and so if you have troubles, they're trying to make it better. So yeah, great side question. Anyway, our HAL Blinky works fine, and that makes me very happy. But let's go ahead and take a look at the next layer then. And we're going faster than I expected today. Maybe we're going too fast, but I don't know. The C6 is definitely the easier one to use for sure. So, oops, what just happened? Now I've lost the comments. That's fantastic. There we go. So let's look at the third layer. Now that we've looked at the HAL layer, which is the board support package layer. And for the Blinky, it's not going to be that different. Let's look at this. Here, you'll notice we still use some stuff from the HAL layer, both directly through embedded HAL and indirectly through microbit HAL, but we're using this microbit v2 package. If you look at cargo.toml, you'll see that there's this package microbit v2 that Cargo downloads and installs. That is a package, that is a library that's specifically customized for our board, the microbit version 2. And so this microbit crate here is that. It's the microbit version 2 package, crate package, and has specific stuff. Here, though, you'll notice at the end of the day, it doesn't look very different here because, we're still just using the HAL interfaces because that's kind of all we have for this board. What we'll see later on is that there are conveniences. The biggest convenience here is that you'll notice that instead of having to know, if we go back to the HAL version, right, we're here at, we need port 0, pin 21, and port 0, pin 28. Those are the pins we need. Well, that required looking stuff up on the microbit schematic and understanding how the circuit worked. Here, we need the pin that's called row 1 and the pin that's called column 1 on the board. And the board support package knows about the schematic of our board, and so it can go ahead and abstract that away through this display pin structure, which makes things easier. And if I run that Blinky, it's not going to behave any different than the old Blinky, so it's going to be hard to tell what happened, but maybe we'll temporarily actually change this to blink faster or something so that we can prove to ourselves that it's actually working. We'll make it be a half-second Blinky now, and it'll blink faster. So let's go back to here. And you'll notice that I forgot to run with release that time. We'll go back in a minute to the pack one and we'll talk about some things with this spin loop delays, but let's go ahead and make sure that this works, and it will. And you'll notice that it's blinking twice as fast now. And everything's good. It all works exactly the way you'd think it does. Let's put this back. And then let's look at the pack crate one again. There's a thing I want to emphasize about this spin loop stuff that I forgot to mention. Then we'll take a quick break. So again, the timing here matters, right? This thing is executing a machine instruction that keeps count of how many steps has gone. It's executing our no-op machine instruction, and then it's executing some instructions that go back and do it again. So we test, we increase our count, we check to see if the count is too big. If it's not, then we do our no-op, and then we jump back and do all that again. So this can be a lot of instructions. And if I compile it without release mode, let's try that. Then when I blink it, oh shoot. It's taking a long time to change, right? Because apparently there's a lot of instructions per step. For this, we could actually look at the instructions the compiler generates for this probably pretty easily. Cargo asm, and it's in what is the name of this crate? It's called Blinkies. Blinkies : wait. Whoop. In pack Blinkies : wait. Let's see what it does. So this is actually a cargo command that you can install. Cargo takes plugins that actually shows you the machine instructions the compiler makes for a particular thing. And whoops. Let's try it just this way. Oh, interesting. Okay, so maybe it's not going to work. That's too bad. It insists on compiling with the release profile, and the release profile optimizes away that function. That's really stupidly annoying that the default's release. Let's try it. There we go. Now we can do it. Where's our wait function? Is it in here somewhere? It should be. Very confused. Oh, I see. There we go. So here's all the instructions. Sorry, that took longer than I thought. Here's all the machine instructions that are executed in the loop of this thing. This may be hard for you to read because it's assembly language, which describes machine instructions. But basically, this loop right here does all this stuff, and it calls the core iter range next function, which is a bunch of instructions. And then it does some instructions to see if it needs to keep going, and if it doesn't, then it goes to some place we can't see. That's interesting. Otherwise, it does a branch to the immediately next instruction, which is silly. And so, yeah, basically this is a lot. Let's see what happens if we compile it in release mode. Whoops. Oh, the instruction gets completely compiled away. Right. So let's see what the program looks like. Whoop. Yeah. Zero, please. There we go. Here's our program now, our whole program compiled in release mode. And right here, it's optimized away the spin weight to just do the no-op instruction. And it looks like it's even optimized away the no-op instruction, which is illegal, so I'm a little bit confused. Oh, no, probably it's that. All right, there we go. Now we're talking. Here's our no-op. So here's our little spin loop here. It's just a few instructions. It just goes around like that. And that is the whole story of that spin loop. So that's why we need to run release, is the bottom line there. Is we need to run release because otherwise our timing loop is terrible. Now, one thing you might wonder is, do we really need that no-op in our spin loop, right? This should be kind of optional, right? We should just be able to spin 4 million times. That should be enough. Why do we have the no-op instruction there? Well, let's try it. And it says, oh, you're not using your no-op. Hey, wait, the light's just stuck on. Well, is the light just stuck on? No, it turns out that it's on half the time. But the compiler sees that loop that doesn't do anything, and it just throws it away to make your program faster. And so now we're switching the LED on and off literally as fast as we can, which means that it's at sort of half brightness, because half the time it's on and half the time it's off, but it's working too fast for the camera to pick. It's flipping too fast for the camera to pick up, and it's even flipping too fast for my eye to see. If you run this program on your microbit like this, you'll find out that it just looks like it's not quite as bright as the LED is supposed to be. So that's why that no-op was there. It had an actual purpose. The compiler's not allowed to optimize it away, so it has to do something 4 million times. We'll put it back again. All right, I think this is a good time to break. I think we are moving faster than I expected us to move, but the binary size. Good comment. Sorry, again, I missed the comments. The binary size is also a big deal. Even if it didn't make your program faster, it definitely makes your program smaller. So if I look at, let's make sure both are built right. And we'll build it without release with the dev profile. Target thumb blah release. That the release target is 648 bytes of code, which is not very much. The debug version, the version that wasn't built with the optimizer turned on, is 5K of code, right? So yeah, the difference is super big in size as well, because the compiler doesn't remove redundant instructions in debug mode. It doesn't throw anything away. Why is it called debug mode? Well, because if you use it with a tool, the debugger, you can actually do some things with that program because it's built more simply. The debugger can understand how the program runs. with the release thing, it's very hard to work with it with a debugger. But unless you're planning to use a debugger, you should just always use the release flag. That's the rule here. So yeah, I think that's a good time to pause for a moment. Let's take 5 minutes and reset a little bit, and then we'll jump on to the next set of topics. I'll talk to you in just a minute here. Okay. Okay. All right, let's come back here. All right. I was just working on the editing up the outline for today, because we're going to go ahead and skip on to the next chapter of the Rust Embedded book. By the way, most of what I told you, I think, is in the Rust Embedded Discovery book. That's, kind of what we're working off of for this course. So if you want more information than the lectures are providing, that's where I would go. Looks about right, probably. I don't know. Okay. I'll show you the screen here in a second when I've got it figured out. I see. All right, so let's see where we are here. The next thing is yeah, thanks for the link. Absolutely. The next thing here, I think, is to go ahead and look at the microbit board support package a little bit more in detail, because like I say, for the next while, we're going to be working with the HAL and the PAC through the BSP. We'll basically be using the BSP as our main source of truth for things. So let me pull up that Rust microbit V2. Let's pull the documentation for the microbit V2 crate. And again, this is all just easily available. You can Google for it. There's nothing secret here. This is the joy of open source, is that all the stuff, you can just go look at it. This is the Rust documentation for the microbit V2 crate. And this is our board support crate that we'll be using. Here's a nice picture of a microbit. No, that's an old microbit. Sorry. I'm not quite sure what on the right and on the left refer to here. Oh, I see. Okay. So this is our microbit. No, this isn't our microbit. Huh, that's odd. Their documentation looks kind of broken, maybe. Maybe this one's the right one. Anyway, so if we look at the microbit crate, the main thing that we are using here is the board structure. And the board structure, you'll notice, has 61 fields. Those 61 fields represent all the pieces of the microbit. This is spare pins that aren't used for anything else. This is the edge connector on the board. This is the pins connected to the microbit's display, which is just those 25 LEDs we looked at before. There's pins connected to the buttons. That's these. You'll notice that your microbit on the front has buttons labeled A and B. Those A and B buttons are what that struct was connected to. One thing about those buttons, while I'm at it, I should just mention, those break off. Yeah, it's the microbit V2 crate that we're looking at. It's labeled it's named microbit. It's really annoying, but what we're looking at is the crate named microbit from the package microbit V2, which is just a mistake and somebody did it wrong. It's frustrating, but there we are. So one thing I should warn you about the buttons. Yes, there's a separate microbit V2 package. So yeah, now we got to talk about the difference between crates and packages. Let me flip back to the screen for a second. the crate here is named microbit. The package here is named microbit v2. That's what's on crates.io. But there's also a separate name for the stuff in the crate, and that name is microbit. I don't know of any other crate in the whole Rust ecosystem that does this, but here we are. And so the package you're looking for on crates.io is the microbit v2 package, and that's what this is the documentation for. And that's why it had that weird note at the beginning about, are you sure you're looking at the right documentation? The microbit v1 is very old now, and you probably will never find a microbit v1 in the wild. They were just a smaller, simpler, dumber version of what our board is. So what I was going to say before I forget, though, is these buttons here on the microbit, the A and B buttons, they break off really, really super easy. They're not expensive to get a replacement for, except that you can only buy the replacement switches usually in rolls, in reels. So then it does get expensive. So be careful with the buttons on your microbit. I actually put hot glue around the buttons on some of my microbits to keep the buttons from breaking off. But I also bought a reel of replacement buttons. Just know that, you know, they're sturdy. I mean, it's like they break off if you breathe on them or anything, but do know that they can break off if you wham them real hard from the side. I wish they were more sturdily mounted. So anyway, there's all this stuff here, most of which we don't even have to think about right now. This is all the peripherals on the microbit chip itself. And then there's these pins for the internal and external I²C. This board support package is a little weird because it doesn't actually provide board support for a whole bunch of the stuff you'd think it would. If I go to the modules here, you know, there's a bunch of hardware external to the microcontroller on our microbit board that it doesn't actually provide support for. And that's the thing we should probably fix at some point, but we haven't yet. So yeah. Anyway, I think the next thing to poke at is some of the stuff from the next chapter of the book. So let's go off to the book here. Embedded github.io/discovery MB2, and here's our discovery book, and we're now up to we're past chapter 5 and up to chapter 6 of all things of this. We already did this, though. All right, so we passed chapter 6 and on to chapter 7. So here's what we're trying to do. This is the project that we're working through in this next section. And sorry about all the flashing and stuff. Hopefully that shows up okay. Is to actually spin a light around the edges of the board like this. And to understand what we need to do here, it's worth going back to the schematic for a minute, because there's a little clever thing that's happening here that we need to understand. In addition to emitting light when electricity flows through them in the forward direction, LEDs are diodes, which means they have another interesting property, which is that electricity can't flow through them in the backward direction. If I put 3.3 volts on call 1 and 0 volts on row 1, nothing will happen. Electricity won't flow because diodes are like one-way valves. They only let electricity flow one way. And what the people who designed the hardware did was took advantage of that by designing what's called a matrix here. If I want to light up say, this LED, then I can put electricity on the row 2. I can put plus 3.3 volts on the row 2 pin, and I can put 0 volts on the column 4 pin. And when I do that, row 2 column 4's LED will light up. But if I have any of these other columns set to 0 volts, then their LEDs will light up too. If I have any of these other rows set to 3.3 volts, then their LEDs will light up too. So the point is, if I want to light up just one LED at a time, I set this row positive and all the other rows grounded. And then I set this column grounded and all the other columns positive, maybe. And when I've done both those things, this is the only LED that can light up. I can light up exactly one LED. So now we know how to do what we need to do for our program, right? We can, if we look at what we were trying to do, let's see right here. You see, there should be a slowed down version somewhere, I think. Maybe not. I can't remember. Yeah. You can see what's going on here. We just pick one LED at a time and light it up like that. But, of course, it's a pain in the neck to do that, because now I have to have all the control of all the row and column pins, and I have to figure out which one to turn on when and stuff. But I can do it, and when I do that, then I can make the display do something interesting. So let's take a quick look at what that looks like. Let's go back here. What we're going to do, instead of fiddling around with the pins directly like that, is we're going to use the so-called display functionality of the microbit. The microbit board support package provides a display that lets you control how these lights look. And to understand how that works, we should go back to the schematic again real fast. So I said we can really only light up these. We really, if we want to have control over an LED, full control over an LED, we should only light up one LED at a time. And that's not quite true, right? I could light up whichever pins I want in a row all at once by controlling the column wires. But if I got to be careful, because if I try to turn this one on by putting this high and this low, and I also try to turn on this one by putting this high and this low, then these other corners will also light up, right? This will light up, and this will light up. And so what we do is we actually light up a row at a time. And we light up whichever LEDs we want in that row, and then we turn it off and light up whichever LEDs we want in the next row. This is called scanning out the row. So we're going to turn on, we're going to scan out the first row. We're going to scan out the rows. We're going to turn on what we want in the first row, and then turn it off and turn on what we want in the second row, and then the third row, and then the fourth row, and then the fifth row. And if we do that fast enough, it'll be just like that thing we saw earlier. It'll be happening so fast that we can't see it switch, and all the LEDs will take turns being on, and it will look like everything's cool. So if we go back to our original thing here up at the top, the slowed down version that I was going to show you. What's going on here is that it's actually scanning out each row and column here, but it just so happens that one LED is on. And if you go back to the first thing, what we're going to do is turn all the LEDs on, but we're going to turn them all on by scanning it out. And the way that we're going to do that involves some more stuff from Rust that we haven't talked about yet. So let's go talk about that and talk quickly about a couple of things that we want to do. So and again, this source code is all available. You can go play with it when. And where were we? 07 LED roulette. So here's the example from the book that we were looking at. Well, again, the board support package gives us this board struct that we take and make sure nobody else owns it, that contains structs representing all the peripherals on the board. Then we get a timer, just like we did before, because we're going to need it in this case. We get the display struct out of the board, which takes control of the pins, those row and column pins, those 10 pins. Here's an array. This is Rust arrays. We talked about them briefly before. This is an array of arrays. This is an array of 5 arrays. Each of those 5 arrays is an array of 5 numbers. Because Rust type inference, you can't actually see the type here. I kind of think they're U8s, so I think this type might be something like array of 5 U8s, 5 of those. So that would be the type probably that those are, but I'd have to go look it up to make sure. So this is the map sort of that's going to tell us which LEDs we want to have lit up. How are we going to do that? We're going to literally just use the display show routine. We're going to say, hey, display show routine, borrow this timer mutably. That is, I'll let you control this timer for a while. You can use it for whatever you want. And I want you to put this pattern up on the display. That's what this matrix specifies. And I want you to do that for 1,000 milliseconds. That is 1 second. And then we're going to say, oh, put up the pattern where none of the LEDs are lit. That's what clear does. And then we'll wait another second using that same timer because, the display code's not using it anymore. We'll just wait a second. So this should blink on and off all the LEDs once per second. That's what this should do. And the interesting thing about this is why does display.show need access to a timer? Well, it needs access to a timer because it's going to scan out the display, right? It's going to go light up the first row for a while, then the second row for a while, the third row for a while, the fourth row for a while, the fifth row for a while. And each time it's going to light it up for a specific amount of time. I don't remember what the refresh rate is by default for the display code, but it's pretty fast, probably 30 or 60 frames per second, rows per second, probably 5 times that, probably 60 times 5 is 300 rows per second. And so it needs a timer to do that precisely. And so we're loading it one. This is Rust's borrowing model, mutable borrowing model, and it works very well. So if we run this lighted up example, you'll notice that this source code is in the examples directory. Light it all is, and we run that. That's doesn't mean much. It just means that we run it with the -- example thing. And if we run this, let's go look at what we're doing. If we run this, look at that. Once per sec, spends a second on, then a second off. And you'll notice, because the camera itself scans out at a particular rate, that you can sort of see the LEDs, sort of not lining up evenly. That's because the rate at which the rows are being scanned on the microbit interacts with the rate at which the camera is scanning out an image. And so it lets you know that also you'll notice that it's a little dimmer than it would be if when we just was doing the blinky, we're doing the blinky the obvious way. And that's because the LED's only on 1/5 of the time than it otherwise would be. And so, and the good news is that brightness isn't really linear. And so being on 1/5 of the time is good enough to make it pretty bright. And you don't have any problems seeing any of this. It's pretty visible. And yeah, like I say, if I look at this on my microbit with my eyeballs instead of the camera, it looks pretty bright and it just blinks on and off and you can't tell. An interesting thing you can do if you want to see the scan out is that you can do this. Oh, sorry. You can do this, and you can sort of see that as it wiggles around. I'll try it again. As it wiggles around, you can sort of see that it doesn't, some of the stuff's on, some of the stuff's off. It doesn't look like it's blurry. It looks like it's blinking. It just looks like it's separated. If I do it sideways, it just gets blurry because it's being scanned out by rows. But if I do it vertically, then it looks all pointy because it's being scanned out, and there again, the camera and the thing are interacting. And it's also noticeable. You can do that in person and see that effect too. That's a thing. So yeah, absolutely. So that's how you use the display part of the BSP to control the LEDs. We're using here what's called the blocking display. What blocking means here, let me switch back to just the screen. What blocking means here is that while we're displaying, we can't do anything else. Our code is sitting here waiting for the display show routine to finish running and not able to do anything. The microbit also has support for a non-blocking display, and we'll see that later, but we won't play with that today. So we're sitting here running this non-blocking display code, but what was the real goal here? The real goal was to do the make the thing spin around, right? And so we're going to have to modify this program essentially to do the spinning bits, right? And let's take a look at that. So what we're going to have to do, I guess, is we're going to have to modify that display array. It looks like once per second or maybe once per half second. Oh, no, sorry, because we're in the slow mode. In the fast mode, it looks like it, I don't know, it's hard to tell, maybe 10 times per second. We change which LED's on, and we can do that with the blocking display just like we did before, but we're going to end up modifying the array to say which LED is supposed to be turned on right now. I will show you what that looks like. Which is this. Solution. This is probably the dumbest way you could do this. There's no loops or anything. I just make, again, an array of Rust tuples. A tuple in Rust is a structure that is like a struct, except the elements are not named. And so this is just, oh yeah, this is the row and column position that you want to turn on first. And then you want to turn on this row and column second, and then this row and column third, and so forth. And I just wrote that all out to describe what should happen. I didn't do anything clever or interesting. You notice the tuples here have a type, they're U size, and that I had to count the 16 elements in the array, which is really super annoying, but it does mean that I got the count right? There's 5, 10, 15. Wait, why are there 16? That doesn't even seem right. Oh, there should be 5 there. Oh, right. 5 and 4 is 9, and 4 is 13, and 3 is 16. Yeah, that makes sense. So that's the 16 elements that are around the edge, is those. So down here, where we actually do it, we set up a mutable array, an array we can change to represent the display. And then we keep track of which, of what the previous LED was that we had turned on, because we want to turn it off when we turn the current one on. So we, each time through the loop, we turn off the LED we had on, the entry in the display array for the LED we had on before. We turn on the entry for the LED that we want to turn on now. And we're doing that by taking this tuple, we're iterating over the pixels, right? This is pixels.iter means just, means iterate over the array, element by element. Which array? This array, right? So it says, oh yeah, start with 0, 0, then 0, 1, then 0, 2, and so forth. And you'll notice this is all in a loop. So when we get done iterating through all the pixels, we just go start over. This .0 and .1 refer to the first element of the tuple and the last element of the second element of the tuple, just like you'd think. These are actually constants, so you can't use an expression here. And so you say last LED.0, last LED.1, we'll turn that off. Current LED.0, current LED.1, we'll turn that on. And then we'll just block. Apparently for 30 milliseconds, we'll block, showing that pattern with a timer, just like we did before. Nothing surprising here. And then we'll remember which LED we had less. Why is there a pointer here? Because it turns out that this current LED is actually a reference. It's not a value. I'm not sure that's even true anymore. We might be able to get rid of deleting that. I'm going to try it and see what happens. Let's find out. It'll be exciting. Cargo build release. Nope, it really wants you to pointer there. Okay. Let's try into iter here. Yep. Okay. So this says, don't give me the references to the tuples to the elements of the array. Give me just the elements of the array. These are copyable. Tuples are copy if their elements are copy. So it just makes a copy now of that. I think that's cleaner. I like it better. And I might not even need the into iter anymore. Let's find out. Yeah, it's fine. All right. So we're just going to loop over the pixel positions and do that thing. And that's going to be how our program runs. So let's try it and see what it works like. We'll go back to our display here. And we'll just say, since it's the main program, we can just say this. And we will get, hey, look at that. It's racing around. It's hard to see on the camera, but it's actually moving quite smoothly. Because it's going so fast, the camera's picking up multiple pixels at once. The thing's moving faster than the camera can scan out. And so it looks a little janky. Let's slow it down so that we can see it's working right. down here, this 30 milliseconds could easily be 60 milliseconds or even 100 milliseconds. I think 100 milliseconds is plenty fast. And now you can see it moving pretty smoothly around. There's still a little bit of scan out issues. You can see it moving pretty smoothly around now. Let's actually slow it down even more. What the heck? If we do 200, it'll be really easy to see. Yeah, now it's just moving around fairly smoothly. And you can see that it was always moving around fairly smoothly. It just was hard to see because the camera was messed up. So that is LED roulette. Very simple thing. In the process, as usual, of cleaning it up, I cleaned up some things that we'll go ahead and push to this repository, and the book will get updated. You can imagine doing all kinds of fun stuff with this display. It's not as good as a real screen, obviously, and it would be nice to be able to display text in some non-terrible way. But it was cheap, and it lets you play with LEDs, and so that's why they did the microbit this way. Next time, we'll pick up input and start playing with the buttons on the front of the microbit. And then we'll go on and poke at some of the other hardware that's on the microbit. That's the plan for Wednesday. So I will, unless there are any questions or concerns, I will see you on Wednesday for the next installment of our adventure. Sounds good? Cool. Thanks much. It was fun. Remember, well, that reminds me, one last thing before you go. Zula.rustedu.org in channel Rust Africa embedded, I believe. Let's go look. One moment, please. There we are. Yeah, Rust Africa embedded. You can go here and get signed up. And if you have any questions or want help with anything or want to talk about anything, that is absolutely a place to do that. I think it's a fun place for people to meet. A few people signed up, but I haven't seen any traffic much there. Please use that as a resource. The URL was broken for a while, so maybe that was why people aren't there as much as they could be. But it should be working again now. Cool. I will talk to you all again very soon.